Hi, welcome back to my channel. In today's video, I'm going to show you a generalized form of the alternating series, where you have a polynomial numerator and obviously a geometric term in the denominator, where a is some value greater than 1. We need that condition of greater than 1 to verify that it's convergent. You may see that this is a similar video to my very first one, where I didn't have the alternating series, and we're going to find in the end that we end up with a very similar but still beautiful result. Okay, so with our condition of a greater than 1 and c is a constant, we're going to first find the solution form of the constant term in the numerator, and then we're going to build to the linear term and then the quadratic term, and then hopefully generalize to a pattern. And so like before, if I list out all the first, let's say 6 terms here, I can then try to reorganize this, and we can reorganize the list here because we know this is convergent. And so one thing we can recognize is every odd term is negative and every even term is positive. So let's regroup it in that form. And now with simple value evaluations on the numerator, we can see that we have negative 1 over a to the 1, negative 1 over a cubed, negative 1 over a to the 5th. And of course, that would continue for all the negatives until we get to the positives, which is 1 over a squared plus 1 over a to the 4th plus 1 over a to the 6th, and so on. And so now that I have two distinct groups that are independent of each other, we can actually identify a series that represents each group. So in the first group, we have negative 1 in the numerator every time. In the denominator, we have an a every time. And the only thing that's actually changing is the 1, 3, 5. And to represent 1, 3, and 5, which are odd numbers, we just need 2n minus 1. So that would become the summation of negative 1 over a to the 2n minus 1. On the right, we always have 1 in the numerator, but then we have 2, 4, 6. And so to represent 2, 4, 6 would just be a to the 2n. That way it starts counting at 2 and then doubles and then triples and, well, doubles every time. So 2, 4, and then 6 each time from each of those inputs. And so now we get our rewrite. So therefore, that alternating series up top there is equivalent to stating these two summations. But the cool thing is we established in my very first video a way of calculating these two summations once I get them in the proper form. So in the denominator here, I have this minus 1. We don't want that. And so we can just pull out an a. And just for simplicity, I want to go ahead and pull out the minus with it. Now, why that helps me is you'll notice now the two series on the right here, the summation of 1 over a to 2n, and on the right it says the summation of 1 over a to the 2n. It's the same summation. So I can combine those summations because on the right I have one of them, and on the left I have negative a of them. And so if I combine those two summations up, I get c times 1 minus a of the summation of 1 over a to the 2n power. And we really like that because we have established facts from my very first video. And here we can see that we're dealing with the very first case, a constant over some a to the n power. In our case, the a is actually a squared. And so when we plug in our constants of c times 1 minus a for the c and the a squared for a, we end up with that substitution. And part of the beauty of this is I can actually factor apart the a squared minus 1. And then I can see that 1 minus a is actually a minus 1 when you pull out a negative. And it simplifies and cancels down to something rather nice. Negative c times 1 over a plus 1. And you may notice that these two are very similar in their general form. And we're going to see that pop up multiple times. In fact, it's how we're going to generalize later. So now let's look at the linear term of just c times n. Like before, we're going to list out all of our values for the first 6 terms and try to see if we could find a pattern. Reorganizing it to negative and positives because that's been so good for us lately. And then doing some calculation, we could see that we end up with negative 1, negative 3, negative 5 over a to the 1, a to the 3, a to the 5, respectively. And on the right, we end up, of course, with 2, 4, 6, a squared, a4, a6. And so we just need a way to model each of those calculations. And we already talked about the 1, 3, 5 being odd numbers. So that's 2n minus 1. And 2, 4, 6 are even numbers. So that's a to the 2n. For the numerator being negative 1, negative 3, negative 5, you just distribute that minus in through the 2n minus 1, giving you negative 2n plus 1. And so now I have my more compact summation form that's much more similar to our identities that we've already established. So now notice I have a to the 2n minus 1, but of course we want them to have the same general base here. It helps to combine things out. So we're going to pull out the a. And so now I have my summations of a times negative 2n plus 1 over a to the 2n. And then I have a summation of 2n over a to the 2n. So I'm going to break apart the first summation here into two different summations. That way we can actually have linear summation and the constant summation, and we can see how things can combine. And so in the first expression, we have a times the summation of negative 2n over a to the 2n. And of course, that a has to distribute to both of the summations. So a times the summation of 1 over a to the 2n, plus my right-hand side of the summation of 2n over a to the 2n. If I bring that negative out front, I'll then have two identical summations, allowing me to combine these first and last summation. So I have 1 over on the right, negative a of them on the left, meaning I have c times all of 1 minus a of the summation 2n over a to the 2n, plus a times the summation of 1 over a to the 2n. And so that original alternating series is able to be rewritten in this expression. And now we can employ our facts that we know. We now have a 2 and that 1 minus a as a constant. So I can just plug that in for c. And then we get our expressions following 1 over whatever our denominator value is, in this case, a squared and a squared. In the second case, the a times summation of 1 over a to n, that's referring to the first situation. And so a and 1 are our constant, and then a squared goes in the denominator. Plugging everything in, we end up with this expression. And now if I do the same kind of, factoring out and then breaking everything down, I end up again with this nice simplified version of c times negative 1 over a plus 1 plus 1 over a plus 1 squared, which again, comparing it to, because I was dealing with the cn version, comparing it to the original summation of cn, we see they're very similar in form. We still have 1 over a something to the 1 power 1 over a minus 1 something squared. In this case, it just happens to be a plus instead of a minus, and we have this negative value. So we're going to explore one more case, the squared case, and we're going to see hopefully a similar thing happen again. And then we'll try to extend this. So now we're going to deal with the squared version, like I just said, listing out our values, calculating those values, and moving all the negative versions to the front, all the positive ones to the back, because again, that seems to keep working for us. For the negative versions, we see that we have 1 squared, 3 squared, 5 squared, 7 squared. So we're dealing with that 2n minus 1 because they're odd being squared on the numerator. On the right here, we have 2 squared, 4 squared, 6 squared. So it's that 2n being squared. And our denominator is the familiar 2n minus 1 on the left and 2n on the right. And don't forget to include the negative for our first version of the series. And so that, of course, simplifies down to this expression. And now that means that this original expression up top can be rewritten as the one on the bottom, but we can do better than that. We want to put this in the exact form that we're used to. And so, of course, I'm going to pull out my a to get me a 2n on the bottom, and I pull out the negative so we can start having these two series look similar. Let's go ahead and FOIL out our numerators, and we end up with the 4n squared minus 4n plus 1 for the first one and 4n squared for the right. And here we can see we're definitely going to end up with two identical series once I break apart this one on the left. So let's break it apart. And so I have the negative a being distributed to all three series, and I have the 4n squared minus 4n and 1. And so we see we have the first and last expression identical now, so I can combine those and get rid of one of the series. And again, I don't have to. I could actually go ahead now and substitute into our facts, but I like to do that with as few summations as possible, so I will combine and simplify. You'll also notice I have a negative a and a negative 4n. I'm going to go ahead and bring out the negative, giving me the following expressions. So I have 1 minus a, and of course the negative a, negative 4 becomes positive. And then one more thing I'm going to do this time is just to try to go ahead and bring all the constants in. So it's going to be very similar to our form, and it keeps all the parentheses down a little bit, essentially. So I'm going to bring the 1 minus a and times it by the 4. I'm going to bring in the a on the second term, times it by the 4. And the negative a, just the a itself, will times the 1. And there we go. So we now have it a little more clean, a little nicer when we do our substitutions. And again, we know the following. We know for the n squared case, whatever constant you have will go for c. And then we have all the values substituted in. And again, a squared is in our denominator here. So it's a squared minus 1, a squared minus 1 squared, a squared minus 1 cubed. In the second case, our constant is 4a. So it goes 4a, 1 over a minus squared, 1 over a minus squared minus 1 squared. And in the last case, our constant is just a in the numerator. So we have a, 1 over a squared minus 1. Plugging everything in, and of course, keeping our minus sign from the summation, we now have our wonderful expanded solution for our answer here. And if we choose to simplify it, we get a very pretty solution set here that represents the final solution of anything in that original form, assuming it's convergent. And notice that it's very similar again to our original form, our cn squared over an. By adding the alternating series component, we get almost an identical solution, just slightly different. So now let's compare all those solutions and see if we could generalize to some kind of pattern that's happening. And so these on the left are our 3 facts we established in our very first video. And the ones on the right here are the ones that we just found. And if we look at them, let's see if we can identify some kind of relationship. Well, one thing you may notice in the denominator is every a minus 1 is exactly the same, but a plus 1. Like the power structure is the same though. For the constant term, we have a minus 1 to the 1 power becomes a plus 1 to the 1 power. In our linear Cn term, we have a minus 1, then a minus 1 squared, then it's a plus 1 squared. So it's keeping the same general form, just plus instead of minus. But all the power structure stays the same. The second thing you may notice is all the numerators were identical. When it was a 1, it was a 1. When it's 1, 1, it's 1, 1. But then when it went 1, 3, 2, it was still 1, 3, 2. So the numerator values never changed. Then the last thing you may notice is that the first term was negative, then it went negative, positive, then negative, positive, negative. It appears to be alternating. So in word form, that's essentially what I'm suggesting. And so now what we're going to do is what anybody would do, is trying to experiment and just see if we kind of extend the table, does it still hold true? And so we're going to first just find the 3rd, 4th, and 5th. And we found that very first video a very fast way of computing these values and extending the table. And so feel free to go back and watch that video if you're not familiar with how I'm calculating these as I did. And so if our conjecture is right, what we would say is the first term would be negative, and then positive, negative, and positive, and all these a minus 1s become a plus 1s. So this is just the conjecture. Second case would be negative, positive, negative, positive, negative, which you can see on the right, and all the a minus 1s become a plus 1s. And of course, all the coefficients stay the same. And then again, negative, positive, etc., with a plus 1 on the bottom, and all the coefficients the same. And now what we're just going to simply do, we would throw this in Wolfram Alpha, and we would check our work. And you'll see, if you look at the partial fraction expansion, it is in fact always the same. It is correct. This technique works for extending the alternating series. So what we found, if we use our technique for deriving these numerators, it will always be a plus 1 to a power higher. So if this is a 5, it goes all the way out to 6. When it was a 4, it goes all the way out to 5. And the only difference is from the other form, the p of n over a to the n, is that the values alternate, negative, positive, always starting at negative because of n equals 1. If you change the index, it does change the order. And in fact, this will extend to any p of n if it's an alternating series problem. But now, I did not in any way go through a rigorous proof to prove that this extends to all p of n. I'm telling you it does. Feel free to go through and verify that claim on your own. Maybe one day I'll make a video on formalizing an official proof for any P of n. But for now, this video is long enough and I'm going to stop here. Thanks everybody for watching and have a wonderful day.